we start the chat about the renal system today. And we're not going to go far, but to be honest, for the future, like for nursing, that's pretty important, and there are some concepts that I want you to very clearly understand. We're going to start with anatomy of the renal system, and anatomically, its gross anatomy is super simple, really. So you have two kidneys, okay, and right and left, and you can see that right kidney a little bit lower, because there's a lever here, which kind of doesn't let it get any higher. So the main function of kidneys is to produce urine. Okay. Urine is drained from the kidneys through the ureters into the urinary bladder. Okay. And from the urinary bladder is served to accumulate urine, so we don't pee all the time. And then urine is released from urinary bladder through the urethra. So far, does that make sense? This basic whole story should be pretty simple. Now, the blood supply. Kidneys receive about 25% of the cardiac output. So you can see that renal arteries and renal veins are a pretty substantial size. Renal arteries branch off the abdominal aorta, and renal veins drain into the inferior vena cava. Kidneys are retroperitoneal organs, so they're located closer to the posterior wall of the abdominal cavity, and any kidney abnormality, like inflammation, kidney stones, stuff like that, manifests itself as the flanking pain in the posterior aspect of your body. Now that's the cross section of the kidneys, and you can see several, proofs of what I told you. So first of all, kidneys are retroperitoneal. Kidneys are surrounded by several layers of connective tissue, starting with a fat. Okay, so fat protects kidneys, cushions them, and perirenal fat, the fibrous capsule of the kidney, it's pretty tough, it holds kidneys together, protects them structurally, organizes them. Now let's take a closer look at the interior anatomy of a kidney. Kidney has two main layers, the outer cortex and the inner medulla. All right? You can see that there are some substructures both in cortex and medulla. So what are those? The darker triangular shaped structures within the medulla are called renal pyramids. The elongated extensions of the cortex, called renal columns. Essentially, the function of the renal pyramids is to produce filtrate. Well, technically speaking, at the time filtrate leaves renal pyramid, it is already urine. Urine from the renal pyramids accumulates in the space between renal columns called minor calyx. So in this image you have 1, 2, 3, 4, 5, 6, 7, I believe, minor calyces. It's just a name for the space. From minor calyx or minor calyces, urine flows in these larger spaces that are called major calyces. And from major calyces, urine accumulates in the renal pelvis, from where it drains into the ureter. So to organize the sequence of urine flow, it's renal pyramid, minor calyx, major calyx, renal pelvis, ureter. Does that make sense?
So what is the point of the columns then? They just
extensions. I mean, cortical nephrons, well, we'll get to the nephrons, but cortex does participate in the production of urine, but essentially the very last step in the urine production is medulla. Ultimately, medulla is what regulates urine concentration, for instance. Okay? Essentially, urine basically is released from the papilla of renal pyramid. Okay? So I mentioned the word nephron. Nephron, shown here, is the elementary functional block of kidney. It means that nephron is the smallest unit that actually produces the urine. Does that make sense? Okay, so there are three main processes that occur in the nephron. Glomerular filtration, shown here on the number 1. Tubular reabsorption, number 2. And tubular secretion, number 3. So let's define what's going on in few words. Let's define what's going on. Where are substances moving in all these three processes? So in filtration, substances are moving from blood to filtrate. In reabsorption, substances are moving from filtrate into the blood. And in secretion, substances again move from filtrate to, from blood to filtrate. My bad. From blood to filtrate. So far, that idea of movement. Blood to filtrate, filtrate to blood, blood to filtrate. Usually I compare this to the process of tidying up your house. So what kidney does is tidying up your blood. How it does it? It collects virtually everything that blood has and throws it away. Meaning moves it to the filtrate. Then it goes through the filtrate. Your kidneys go through the filtrate like you go through the pile of stuff that you decided to throw away, and you pick something that you could still use and you take it back. Does that make sense? And then kidneys take a second look and decide, no, I don't want to keep this. I'm going to secrete it. So that's you going through the pile of clothing that you just brought back into your closet, saying, no, I don't need that, no, for sure, and throwing it back into the garbage pile. Does it make sense? That whole idea of going back and forth, sorting out stuff that you need and stuff that you don't. Okay, we're good? So you can imagine that the amount of fluid that kidney process every day is enormous. So it's about 180 liters of fluid is processed by these two kidneys. Okay? We're good? And I'm talking about plasma. I'm not talking about formed elements. We're talking about fluid, right? Remember that out of those 5 liters of blood that you'll have, plasma constitutes only about a half. Okay? So, what I'm trying to tell you is that kidneys filter 180 liters of fluid every day. And despite that, they produce only 1.5 liters of urine, meaning that they are incredibly efficient. Does that make sense? So what we're going to do, we're going to figure out how kidneys manage to regulate the amount of fluid and concentrate the urine to the extent that you lose only about 1.5 liters of water a day. Kidneys essentially not only filter, they also conserve water. Does that make sense? Good? Okay. Now, nephron. What does it consist of? So first, it's a renal corpuscle, which consists of glomerulus, a bunch of capillaries, and glomerular capsule. Renal corpuscle is responsible for the filtration. Okay? Then you have proximal convoluted tubule, the nephron loop, and the distal convoluted tubule. The main processes that occur in these parts are reabsorption and mainly in the distal convoluted tubule, secretion. Okay, so far, before we move on, do you understand the 4 parts? The renal corpuscle, proximal convoluted tubule, nephron loop, distal convoluted tubule. We're clear? Okay. Now this structure right here, that is called a collecting duct, technically is not a part of a nephron. Think of it as the main river and all these tubules as individual tributaries. Does that make sense? So single collecting duct can collect urine from multiple nephrons. This is why it is not considered a part of a nephron. But there are some pretty important reabsorption processes that happen in the collecting duct that we're going to be talking about. Any questions so far? Good? So this is, unfortunately, I didn't have the individual images of these 2 types of nephrons. So this image is a little bit crowded, but I will try to explain the difference between those 2 as good as I can. So you can see that there are 2 types of nephrons, definitely 2 types. Cortical nephron on the left and juxtamedullary nephron on the right. So what is the difference between these 2? Cortical nephron is located mainly in the cortex, and only rather small nephron loop is embedded in the medullary layer. This veins and arteries, arcuate vein and arcuate artery, they mark the junction between the cortex and medulla. Can you see that? Can you see that only nephron loop is in the medulla, the rest of the nephron is in cortex? Make sense? Now, juxtamedullary nephron. Now, what does the part juxta means? When you say something is juxtaposed to something else. They're next to each other, yeah. Juxtaposed means next to each other. So juxtamedullary means very close to medulla. And indeed, if you look at this nephron, what you're going to see, sorry, bless you, is that the huge nephron loop is entirely in the medulla, and only a small portion of the nephron is in the cortex. Now, are there any other differences? Yes. So first of all, and we will have to go back and find out something else here. We need to figure out the blood flow through the nephron. Okay, let's take a look at the blood flow. So this is artery. Can you see the artery? Artery here to the left of the nephron. It's a radiate artery which branches into afferent arteriole. The word afferent, generally speaking, refers to something that enters. Yes, that enters. So afferent arteriole enters the glomerular capsule and branches, I'm sorry, into glomerular capillaries. Can you see that? Glomerular capillaries then merge and form efferent arteriole. The word efferent in this case refers to something that leaves, yes. So afferent arteriole enters the glomerular capsule, forms a capillary bed, glomerular capillary bed, and then glomerular capillary bed drains into efferent arteriole. Do you see something strange here in this capillary bed? Think about general structure of like the generic capillary bed and compare it to this one. Bingo, no veins. So glomerular capillary glomerular capillaries are supplied and drained by arterioles. Does it make sense? So that's unique. Now, one more question. I'm kind of running ahead of the train, but one more question. Blood pressure. Where is it higher? In the arteries or arterioles, or in the veins? Arteries, yeah, or arterioles. So, look at this. This, the afferent arteriole, blood pressure is pretty high, right? Efferent arteriole, blood pressure is pretty high. What about blood pressure in the glomerular capillaries? That's a simple question. Should be high. Well, higher than regular capillaries, right? It turns out to be true. And if you think about the function of glomerular capillaries, it makes perfect sense. What happens here? Filtration. Look, I told you before, it's the end of the semester and you still can't get used to the fact that if I ask you a hard question, I will tell you that's a hard question. Whole question is simple. Filtration. Anyone has a Brita filter at home that you pour water in? When it filters the fastest? When you pour a lot of water, when there's a lot of pressure, right? That's the point. Filtration is more efficient when you have a decent pressure. Does that make sense? So that's the reason why these capillaries have unusually high pressure. Now, afferent arteriole branches into the glomerular capillaries. Glomerular capillaries drain into the efferent arteriole. Now look where efferent arteriole goes. Into the, forget about this word, into the capillary, right? Another set of capillaries. Does that make sense? Now, these capillaries, where are they located? What are they close to? The renal tubule. Very good. The renal tubule. Okay? So these capillaries will be surrounding renal tubules. Makes sense, right? And these capillaries finally will drain into the vein. Does that make sense? So if we want to make some kind of a list of how blood flow goes, we have artery, right? That goes into the afferent arteriole, that goes into the glomerular capillaries, which goes into the efferent arteriole, which then forms, I'm going to just put capillaries, right? Because we will talk about the difference, but still capillaries. And these capillaries eventually drain into the veins. That story, does it make sense? That's what we just talked about. It's just put in the form of a flowchart, right? So let's go back to our cortical and juxtamedullary nephron. Let's talk about cortical nephron first. That's a majority of nephrons, and you see the afferent arteriole enters the glomerulus, and then glomerulus is drained by efferent arteriole, which delivers the blood to so-called peritubular capillaries. So peritubular capillaries found in the cortical nephrons. And they function as simply reabsorption and secretion of various compounds. We're clear. Now, juxtamedullary nephron is slightly different. Well, not because of the pathway, but because of the structure. So exactly the same way afferent arteriole enters the glomerulus, delivers the blood to the glomerular capillaries, and glomerular capillaries drain into the efferent arteriole, which enters, you see this network? You see this network of the blood vessels, of the capillaries that surround the nephron loop. This is called vasa recta. Now, the word vasa, what does it refer to? Vasa. Vessels. Yeah, vessels. Okay? Veins are vessels. Recta. Muscle system, AP1. Rectus muscles. It's not a special term. It's geometric orientation. Rectus femoris, rectus abdominis. Huh? Human rectum. What did I show you? What orientation? Huh? Not necessarily. It can be like this, but it's, well, like in the eye, it can be like this, but it's what? Straight. Vasa recta is the straight vessels. And you can see they are organized in some kind of a straight manner. Does that make sense? And you see that they surround, very tightly surround long nephron loop. So the function of vasa recta and nephron loop of the juxtamedullary nephrons is to regulate the urine concentration. When you dehydrate it, that will increase the water reabsorption and your urine will be scant and concentrated. When you overhydrate it, it will decrease water reabsorption and your urine will be diluted and, copious. We clear? So far? Any questions? Okay, good. Just trying to think. Did. So first process that we're going to focus our attention at is the process of filtration. Now it happens in the glomerulus, remember? So that's glomerulus. That's the capsule. Okay, so take a look at the glomerulus. So you see capillaries, can you? And capillaries are surrounded by the cells. These cells, called podocytes. It's a compound word, as many other words in anatomy. Cyte means cell. Podo means foot. Foot, yes, like podiatrist, okay? So these cells, they extend all around the capillaries, okay? Does that make sense? They surround capillaries, forming, and these extensions eventually branch even further, forming so-called foot processes. And you can see that foot processes of the podocytes, they are separated by the very narrow slits that are called filtration slits. Does it make sense? So the capillaries in the glomerulus, they are fenestrated. Remember we talked about fenestrated capillaries. We talked about three types of capillaries: continuous, fenestrated, and sinusoid. Continuous being the least permeable, and sinusoid being most permeable. So glomerular capillaries, the fenestrated ones, are somewhere in between. They have openings called fenestrations that allow the transfer of various chemicals across the capillary wall. Does it make sense so far? Now, those fenestrations is the first filtration system in the glomerulus. Second filtration system are slits, filtration slits of podocytes. Blood pressure pushes water and ions and organic molecules out of the capillary. But in order to leave the capillary and enter into the glomerular capsule, these chemicals have to go in between the filtration slits. In between the foot processes through the filtration slits. Do you understand what I'm talking about? Okay, let me make a little picture for you. So imagine that this is the capillary wall. Those are endothelial cells. You with me? Okay, that's a longitudinal section. That's a longitudinal section. Are you following me? Now, these blue ones would be foot processes. Does that make sense?
The bottom layer is the slits, the filtration slits, underneath the
Foot. Say it again.
the red.
Oh, the red are epithelium. That's endothelium. That's vascular endothelium. So, okay, I'm going to show you filtration slits now. This is filtration slit. Does that make sense? Space between the two foot processes. Is that understood? So when some kind of a chemical gets pushed out, it must go through the filtration slits. If it can, it will end up in the glomerular capsule. If it can't, it won't. Is that clear? Does that make sense? Turns out, I'm sorry, the size of glomerular capsule, oh, there's going to be a lot of misspoken things today, I feel it. The size of the filtration slit is such that only smaller molecules can cross it. Anything like protein-sized or larger cannot get into the filtrate. Does that make sense? Huh? Can you speak up? They don't. Because proteins, look, think about this. Proteins are normal. You see what I'm saying? Protein like albumin or beta globins or gamma globins or some other protein in the blood is considered to be normal. So you don't get rid of the proteins or of the cells that you synthesized or produced, spending a lot of resources and efforts. So proteins and cells will remain in the blood. Normally, in physiologically ideal conditions, the filtrate here, the filtrate here will contain water, salts, and small organic molecules. Now, let me ask you this question while we're at it. Which small organic molecules? Now, that's legitimately kind of, it addresses a lot of our previous material. I would say it's not maybe hard, between medium and hard question. Which organic molecules would you normally find in the blood? Smaller organic molecules. Those are inorganic respiratory gases. Forget about that stuff. That's too small. Bigger than anions and cations. Huh? Carbon is the part of organic molecule. Like, huh? Say. Salt is, it's going to be filtered out. That's ion, okay? It's not organic. Organic molecules. I'll give you a hint. Nutrient. Carbohydrates. Not just carbohydrates. Glucose, fructose, any monosaccharide will be in the blood. Another hint. Product, ultimate product of protein catabolism. Urea. Does that make sense? Different nitrogenous wastes. Am I clear? So those small molecules like urea, glucose, creatinine, fructose, ketones, they will all be filtered out. Does that make sense? Proteins will remain in the blood. Ever heard the term proteinuria? When people have protein, like albumin in the urine, that's the bad sign. And we'll talk why in a second. Okay? Does that make sense? Okay, so let's see which pressures participate in the filtration, form the filtrate. Now, we talked before about the fluid living and entering back the capillary. So we've got practically the same story here with the glomerular capillaries. We have hydrostatic pressure in the capillary, 55 millimeters. Now this hydrostatic pressure in the capillary, what is it essentially? What pressure? Say it. Blood pressure, yes. So capillary hydrostatic pressure in the glomerulus is the blood pressure. You see how high it is? Normally on the arterial end of the capillary bed, the blood pressure is 35. Here it's 55. So those are really high blood pressure capillaries. Now there is a hydrostatic pressure from the filtrate side, 15 millimeters. Can you see that? 15 millimeters. And then there is osmotic pressure, the capillary osmotic pressure. But as you remember, so hydrostatic capillary pressure pushes the fluid out of the capillary. Remember that? Sounds familiar? Osmotic capillary pressure. What does it do to the fluid? Osmotic pulls it in, yes. So osmotic capillary pressure that is formed by the blood proteins, mainly albumin, drives the fluid back from the capillary. Does it make sense?
So the osmotic is the one that's in the center?
Yeah, that's a purple.
The one that's at the very bottom. What one is that?
It will be hydrostatic pressure from the side of the glomerulus itself, capsule. Does that make sense? Because, okay, look at this image in the left bottom corner. What's in the capsule? What's here? What's in the capsule? Is that air, vacuum, CO2? I don't know. Chocolate? What process are we talking about? Filtration. What is the product of filtration? Huh? Just one word starts with F. Filtrate. So what's in the capsule? Filtrate. Okay? Does that make sense? So filtrate exerts some hydrostatic pressure back. Now, all in all, what's the result? What's the net filtration pressure? 10. And its net filtration pressure, this net filtration pressure is directed towards the capsule. Does that make sense? Okay. Now, let's play with these pressures a little bit. Imagine that your blood pressure increases. How does it affect net filtration pressure? Increases, yeah. Because this capillary hydrostatic pressure component goes up. If your blood pressure decreases, it's going to go down, yes. Now, let's say, now I'm going to play with some hypothetical stories. Let's say, and we're going to talk about like immediate effects. Say something terrible happens to your liver and you stop making albumin, so your blood has much less albumin than normal. Which pressure is going to be affected if albumin levels go down? Osmotic. How? Well, I'm asking how it will be affected. If albumin is decreased, how is it going to change the osmotic pressure? Yeah, it's going to go down, and if osmotic pressure is going to go down, what happens to the filtration pressure? Osmotic pressure drives the fluid back, right? So it's going to go up. If you have less protein, to pull the fluid back in the capillaries, less fluid is put back in the capillaries, net filtration pressure increases. Does that make sense? Now let's talk about some real issues. Imagine that somebody, for some reason, has protein in the urine. Now that is a hard question. I mean, it's totally logical. You just have to add one more pressure. If there is protein in the filtrate, which pressure do we have to add? So protein, which pressure? Okay, there are two, hydrostatic and osmotic. If it's a protein, then we're talking about which type of pressure? Osmotic. And if it's a protein in the filtrate, then it's going to be osmotic pressure that drives fluid where? Into the, say it, come on, 50-50. Into the? No. Which osmotic pressure drives fluid in the capillaries? Hold on a second. This osmotic pressure here, I really want us to understand that. Osmotic pressure that we have here in the center. What produces it? Why it happens? Why fluid goes back into the capillaries? What drives fluid back into the capillaries? I'm talking only about osmotic pressure. Huh? Dilute what? What's in the blood that it wants to dilute? Which solutes? Proteins, yes. So osmotic pressure is produced because of proteins, right? Proteins drive water back in the capillaries. Does that make sense? What if proteins suddenly appear in the filtrate right here? There's going to be osmotic pressure that will drive fluid where? Out from where? Out from capillaries into the capsule. Does that make sense? Water will follow proteins. So if there are proteins in the filtrate, then people will start losing water. They will start becoming dehydrated. Does that make sense? The net filtration pressure will increase because there will be an extra pressure that will drive the fluid into the filtrate. Does that make sense? Do you understand what I'm saying? We're kind of adding that pressure is abnormal. It shouldn't be there. There should be no osmotic pressure. Your filtrate should be protein free. Now, why it may become not protein free? Imagine that you have a filter of sorts and you decide to filter the water that comes out of your garden hose, okay? And you put that filter on at the end of the garden hose and you start opening the water. And it says on the filter, I don't know, it works until 3 bar pressure. So set at 3 bars and it filters just fine. And you attach it to the hose really, really well, okay? Really well. Then you decide, I need it faster. And you go from 3 bars to 6. And filter is attached really well. It's not going anywhere. What's going to happen to the filter? Huh? It's going to break. It's going to burst. Does that make sense? So if people have consistently high blood pressure, basically hypertension, their capillary pressure is consistently higher than normal. Does that make sense? You understand what I'm saying? So this whole filtration system, which is not designed for that pressure, will start to fall apart. Filtration sleeves start to open up more, letting protein to go through. Does that make sense? And it will lead to proteinuria, and it will lead to blood composition abnormalities and so on and so forth. Does that make sense? It may also be a result of some kind of an infection. If this capillaries, glomerular capillaries are infected, we call it glomerulonephritis. Infection of a glomerulus in a kidney. And that may damage the filtration sleeves of podocytes, and people have filtration problems. Does that make sense? Please. Well, anatomy of the glomerulus, obviously, but also, please, the filtration pressures. Be familiar with what drives fluid where. Review it again. Remember, hydrostatic pressure pushes the fluid out of wherever it is, and osmotic pressure pulls the fluid in wherever it is. Are we good? So that's actually pretty cool. Glomerular filtration rate, and yeah, we have time to go over glomerular filtration rate and some controls. So GFR, volume of filtrate formed per minute by both kidneys. So it's normally about 120, 125 milliliters per minute. It is very tightly controlled. Does that make sense? Now, what can hypothetically influence GFR? Well, first of all, if net filtration pressure increases, how does it affect the volume of filtrate that is formed per minute? Increases. So net filtration pressure will affect. Now, membrane. That membrane formed by the podocyte and the capillary. If that membrane becomes less permeable, something happens to, I don't know, podocytes. If it becomes less permeable, how will it affect GFR? Decrease, yes. So membrane permeability. And surface area. Well, surface area is gigantic. Okay? It's enormous. So we're not really too much concerned about the surface area. But there are cells that could change the diameter of the glomerular capillaries for a little bit, essentially regulating the surface area. It's not a main factor, but it can happen. Does that make sense? Do you understand what I'm saying? So we've got how permeable the membrane is, how big the membrane is, and how much pressure is applied to that membrane. Now, from the standpoint of kidneys, their function is to maintain GFR. Okay? Because normal GFR, normal glomerular filtration rate, means normal filtration, means normal extracellular fluid homeostasis. It means that water is retained the way it should, ion concentrations are maintained the way they should be, necessary wastes are eliminated, so on and so forth. Does that make sense? So kidneys, the intrinsic controls are oriented at the maintenance of GFR. Now, extrinsic controls, as usual, are focused on the maintenance of systemic blood pressure. Now, let me ask you this. Please tell me. If flow to the kidneys, blood flow to the kidneys, decreases. Now, that's going to be several steps. Each step will be simple. Overall outcome will be amazing. If blood flow to the kidneys decreases a little bit, how does it change the pressure in the glomerular capillaries? If blood flow to the kidneys decreases, it will decrease blood pressure. Does that make sense? If blood pressure decreases in the kidneys, if blood pressure in the kidneys decreases, how does it affect net filtration pressure? Decreases. If net filtration pressure decreases, how does it affect glomerular filtration rate? Decreases. Make sense? So you see, GFR can change, can fluctuate. That's normal, because blood flow will fluctuate a little bit. We good? Now, the question is, what can kidneys do about it? So, intrinsic controls of the kidneys regulate GFR. If GFR will decrease, as in our example, kidneys will produce the response that will increase it. That make sense? And if GFR will increase, they will produce a response. They will basically reduce the blood flow through the glomerulus that will maintain GFR constant. We clear? So intrinsic controls essentially regulate glomerular filtration rate in kidneys at the normal blood pressure in the normal conditions. Are we clear? Extrinsic controls take over when blood pressure becomes dangerously high or low. So the extrinsic controls, override intrinsic controls in the kidneys. Does that make sense? So basically, let me explain. systemic blood pressure is the parameter that can be a question of life and death. Do we agree on that? So if systemic blood pressure is dangerously low or dangerously high, the extrinsic controls, even at the price of the functional kidneys, will maintain normal blood pressure. Do you understand? So basically, they preside over the intrinsic controls at the systemic BP over 180 or lower than 80. Does that make sense? Question?
And will that damage your kidneys overall?
It may either damage the kidneys or it may lead to toxemia, and I will tell you how it may lead to toxemia in a second. Toxemia meaning toxins in the blood. Imagine, so go back for a second here and look at the numbers, and we're going to do pretty easy math. This is the blood pressure in the glomerular capillaries, normal, 55, okay? Now imagine it decreases by, I don't know, 20%. 20% is just easy to calculate, so 1/5 of it. So your blood pressure drops 1/5 from 120. Say your normal mean arterial pressure is 100. Just for the ease. What's going to be 1/5 of it? Of 100? 20. So say your mean arterial pressure goes from 100 to 80. Okay? We're good? It doesn't sound too dangerous, does it? And I deliberately say your normal is 100. So you've got to go down to 80. You're still kind of okay. Does that make sense? Now, that decrease by 20% in your arterial blood pressure, how will it affect hydrostatic capillary pressure? Decrease by what percentage? 20%. What's 20% of 55? 11. 55 minus 11 gives you 44. Now, if this pressure suddenly becomes 44, what's the sum of these pressures? 45. Is there any filtration in the kidneys? No. So in fact, drop in blood pressure by 18% means that you get no filtration. Does that make sense? No filtration means that you cannot normally regulate the concentrations of sodium, potassium, calcium, magnesium, chloride, glucose, urea. You get accumulation of all that crap in your blood, or, you know, it becomes a nuisance. There's a problem. Does that make sense? So that's the answer to the low blood pressure. In the high blood pressure, when your blood pressure is high, what's the first direct renal response? Remember, direct renal response. Huh? Well, yeah, but how? What's the direct response from the kidneys? If blood pressure is skyrocketing, what do you do more? You pee, meaning that you produce more filtrate, meaning that look at this. Let's play it a little bit. Imagine that you're a kidney, okay, and your goal is to maintain GFR. So blood pressure goes through the roof. What happens to GFR? Goes astronomically high. You're a kidney. What do you want to say to the central government? What you going to do to that elevated GFR? Yeah, you want to slow it down. You want to reduce the glomerular blood flow. Does that make sense? But your central government going, no, say no, that's not what's going to happen. No. We don't care what happens to you. You're going to let all the blood to go through. GFR will be through the roof, but urine output will increase, blood volume will decrease, blood pressure will decrease, and we're fine. Does that make sense? Now that elevated blood pressure can totally mess up the filtration membrane here. So yeah, it can damage the kidneys, all right. Does that make sense? Now, what are the mechanisms? The mechanisms are, one is super elegant and simple, another one is super elegant and has like a gazillion steps. And I'm not going to say that it's simple. So the simple one is called myogenic mechanism. So in order to better understand myogenic mechanism, I need to draw a very simple scheme of your glomerulus. So that's afferent arteriole, that's efferent arteriole, that's the glomerulus. On top, do you see that picture? The drawing. What's the difference between afferent and efferent arterioles? One is bigger, yeah. Afferent, the one that delivers the blood, is bigger. Can you see that? And that's why there's such a high blood pressure in those capillaries. We good? Is that understood? Now imagine, we're talking about intrinsic controls. Imagine blood pressure goes up. It's a fluctuation. It's normal. It's like, I don't know, 10 millimeters up. Nothing serious. So elevated blood pressure, how will it affect GFR? It will increase it. Now, elevated blood pressure, what's going to happen to the force that acts on the afferent arterioles? Stretch. Yeah, they're going to feel the stretch. So those mechanoreceptors that are stretched will induce an interesting response. Afferent arteriole will constrict and efferent will dilate. So when afferent arteriole constricts, what happens to the blood flow to the glomerulus? Slow decreases, yes. And when this arteriole dilates, it more out of, right? So constriction of afferent and dilation of efferent all together, they reduce the blood flow through glomerulus. Does that make sense? Lower blood flow, lower GFR. Now, without drawing, tell me, and you can look there, but ideally just imagine this. Imagine that blood pressure drops a little bit, but drops. When blood pressure decreases, what happens to the blood flow through the glomerulus? Decreases. What happens to the GFR? Decreases. What happens to the stretch of arterioles? Decreases. What's going to be the response to the reduced glomerular flow from afferent incoming arteriole? It's going to dilate to deliver more blood in the glomerulus, and efferent arteriole will constrict to retain some blood. Does that make sense? It's called myogenic because the response is essentially produced by smooth muscles of the capillaries. Over the arterioles, I'm sorry. Does that make sense? Now, second mechanism. Okay. Brace ourselves. It's called tubular glomerular mechanism. That's the last thing that we're going to go over today for the renal. That's it. Tubular glomerular feedback. Before we go any further with the tubular glomerular feedback, we need to talk about some types of cells. Okay, never mind. All right, that works. It's awesome. Isn't that cool? Okay, so you see these cells here. This is macula densa cells. Their function is to sense sodium chloride. They sense the concentration of sodium chloride. Does that make sense? Can you see these cells? In these cells. Those are called granular cells. Sometimes they also called juxtaglomerular cells. The function of these cells, in the context of what we're talking about now, is to change the diameter of afferent arteriole. They are essentially smooth muscle cells. And finally, the third ones are mesangial cells. Now look where they are located. They're between macula densa and granular cells. Can you see that? The function of mesangial cells that are connected by gap junctions to provide the communication between the two. We're clear? Do you understand this? Now, one last bit to notice. Macula densa cells, they are the part of which structure? What do I circle? It's the part of the renal tubule, yes. So they are exposed to the filtrate. Does that make sense? That was awesome. Just loved it. First time. Now, first, we're going to go over what happens using the flowchart. Then we're going to draw a flowchart ourselves. All right? So let's do the flowchart first. GFR increases. Blood pressure goes slightly up. GFR increases. Blood flow through glomerular capillaries goes up. Okay? Now, if blood flow, blood flow through the glomerular capillaries goes up and GFR increases, what happens to the amount of filtrate that is formed? Goes up. As the amount of filtrate goes up, what happens to the rate of the filtrate flow? Is it flowing faster or slower? More filtrate means faster, right? Just more water. You open up the faucet. As it flows through the tubule, it has less time for reabsorption of ions from the filtrate into the blood. Is that understood? I usually compare it to like riding a train trying to jump on a platform. If the train goes slow, you have a lot of time to jump back on the platform. If the train goes fast, you have very limited time to jump back on the platform. Does that make sense? So, since reabsorption time decreases, reabsorption itself decreases. Do you understand what I just said? Now, reabsorption is the movement of stuff from the filtrate into the blood. If reabsorption decreases, what happens to the concentration of, say, salt in the filtrate? It goes up because there's not enough time to take it into the blood. Does that make sense? Do you understand what I just said? Now, this increased sodium chloride concentration is sensed by macula densa cells that through the mesangial cells signal to the granular cells to constrict afferent arteriole. When afferent arteriole is constricted, what happens to GFR? It decreases. Does that make sense? Now, last thing that I want to do. We're going to do the same. This time, let's reduce the blood pressure. Okay? Blood pressure goes down. Blood flow via glomerulus. All I ask is decreased or increased. That's your role. It is decreased. And as the result, the GFR is decreased. As GFR is decreased, amount of filtrate is decreased. Sorry for typos. Just really hard to speak, think, and write at the same time. As amount of filtrate decreased, rate of flow for the filtrate decreased. So far, it's really simple, right? As rate of flow is decreased, reabsorption time increases. As reabsorption time increases, the reabsorption itself, now be careful, I'm introducing the new step to make it more detailed. Reabsorption itself, reabsorption time increases, reabsorption increases. As reabsorption increases, filtrate concentration of sodium chloride, the squared parenthesis means concentration, decreases, decreases, and then you've got, sensed by macula densa cells to the granular cells. And what happens to afferent arterial diameter? And what happens to the GFR? Increases. Does that make sense? So this is not kind of important. It is really important. I'm going to ask you a few questions about it on the exam. Okay? And those are the questions that are heavily physiological, and they actually, you need to be able to write this thing all the way through. Does that make sense? Because there will be, the question will be, let's say, what happens when blood pressure, systemic blood pressure, slightly increases? And then I'm going to give you a bunch of statements like GFR goes up or down, flow rate of filtrate goes up or down, reabsorption time goes up or down, sodium concentration goes up or down, stuff like that. Does that make sense? So you have to be able to deduce what's going on. Is that clear? Good?
So these are happening at the same time. Right?
Myogenic and juxtaglomerular responses? Yeah. Yeah,
So
they're not separate.
Like we go through the first part of the tubular, and then the myogenic comes in after the, what is it?
Myogenic response is produced when basically stretch receptors in the glomerulus sense the changed pressure. Does that make sense? Hold on a second. I think I understand what you're asking. I need just to go back. So myogenic response, the sensing part, just think about this. It's a reflex. Basically, it's a reflex, right? You have a sensory input, which is stretch, and you have a response, which is, say, constriction of the afferent arteriole. Does that make sense? So that sensing happens here.
So that happens at like where it said the afferent artery constricts.
So it happens here.
Okay.
Now, juxtaglomerular response, tubular glomerular response. happens here. Because at this point, we're already talking about the filtrate in the tubule, in the proximal convoluted tubule. Did I answer your question?
Yes.
Any more questions? If none, we'll take a break, come back, review the quiz, review the study guide.